Section 4.2, relationships between categorical variables. Table 4.5 presents Census Bureau data describing the age and sex of college students. This is a two-way table because it describes two categorical variables. Notice that age, normally we would think of age as a quantitative variable because it's measured in years or months or days or whatever we may be measuring it in. In this case, it's a categorical variable because we have age groups in which we are putting the students into. Age group is the row variable because each row in the table describes students in one age group. Because age group has a natural order from youngest to oldest, the order of the rows reflects this order. Sex is the column variable because each column describes one of the sexes, either male or female. The entries in the table are the counts of students in each age by sex class. The distributions of sex alone and age alone are marginal distributions because they appear at the bottom and right margins of the two-way table. So if you were asked to do a marginal distribution of sex alone, we would be looking at taking each one of these values and dividing by the total to find the marginal distribution of sex alone within each age group. If we wanted to do a marginal distribution of age group by sex, we would be going then across the row and we would be taking each of these values and dividing by the total of the row. So you can do marginal distributions on the row variable or the column variable depending on which you are asked to do. The percent of college students who are 18 to 24 years old is 62.3%. The reason that we can get that is we take the total of the age group 18 to 24, which is 10,365, divide by the grand total, which is 16,639. Are you surprised that only 62% of the students in the traditional college age group? Do 3 more such calculations to obtain the marginal distribution of age group in percents. So the age group of 15 to 17, if I wanted to do that marginal distribution, I would go back here and look at 15 to 17. There are a total of 150. I would then divide by the grand total of 16,639. So this 0.9 is obtained by taking 150 divided by the grand total of 16,639. 18 to 24 group, again, take the row total of the 18 to 24 group, which is 10,365, divide by the grand total, 16,639. 25 to 34 age group, take the row total, 3494, divided by the grand total, 16,639. In the 35 and older group, take the row total, 2630, and divide by the grand total, 16,639. So that's how we do a marginal distribution. It's either row total divided by grand total, or it's column total divided by grand total anytime we want to do a marginal distribution. The total, if we add all those up, is 100% because each one of the 4 age, everyone is in one of those 4 age groups. So marginal distribution, remember, let's write this down. If it's on the row variable, then it is row total divided by grand total. If you want to do a marginal distribution on the column variable, then it is column total divided by grand total. Conditional distribution of sex given age. If we know that a college student is 18 to 24 years old, we need to only look at the 18 to 24 years row in the two-way table. To find the distribution of sex among only students in this age group, we're going to divide each count in the row by the row total, which is 10,365. The conditional distribution of sex, given that a student is 18 to 24 years old, is given by this. So when we do a conditional distribution, the way that we get these percentages here is I am looking at So I want to look only at females first. So if we go back to our table here, and I'm looking at females, we add up, looking only at the 18 to 24 group. We look at the females, and we divide by the total number of students in that 18 to 24 group. So we have 5,668 divided by 10,365. 5,668 divided by 10,365. Males, I look at the males in the 18 to 24 group. There were 4,697 of them, divided by that row total, which is 10,365. The 2% add to 100 because all 18 to 24 year students are either male or female. We use the term conditional because these percents describe only students who satisfy the condition that they are between 18 and 24 years old. Find the conditional distribution of sex among students for at least 35 years old in the same way. Now looking at the third or 35 year or older row. So again, we're looking only in the 35 or older row. We see that there are 1,660 females. Total of that row is 2630. Divide those out. That's how we get the 63.1%. For males, there are 970 out of the 2630. So that's how you do a conditional distribution. Whatever variable it is you are conditioning on, you are looking only at that row or column for the condition. In this first case, the condition was that they were in the 18 to 24 group, and then we wanted to find the conditional distribution of sex within that age group. So we take that one cell total of females in the 18 to 24 and divide by the row total that we are conditioning upon, which is that they are in the 18 to 24 group. We can also do conditional distributions going the other direction. This time we are going to condition on the column variable. What is the distribution of age among college female students? Information about women students appear in the female column, so look only at that column. To find the conditional distribution of age, divide the count of women in each age group by the column total, which is 9321. There's the distribution. So again, if we look at the female column only, we look for age 15 to 17. So we're back here at our table. We see that in this case, we're looking only at the female column. We have 89 females in the 15 to 17 group. Since we are conditioning on sex now, we're looking at a column variable. So we're going to take the cell total, divide by the column total. 89 over 9321. 18 to 24 group, 5668 over 9321. 25 to 34, 1904 over 9321. And finally, 35 and older, 1661 over 9321. So now we're conditioning on a column variable. Looking only at the male column, we can do the same thing. We can find the conditional distribution of age given sex. In this case, we're conditioning on men. Look at the column total of men is 7,317. The number of men 15 to 17 is 61 out of 7317. 18 to 24, 4697 over 7317. 25 to 34, 1589 over 7317. And finally, the last group, 970 over 7317. Comparing these two conditional distributions shows the relationship between sex and age in another form. Male students are more likely to be 18 to 24 years old and quite a bit less likely to be 35 or older than the female group. Okay, looking at our first example here, 26. How is the hatching of water python eggs influenced by the temperature of the snake's nest? Researchers assign newly laid eggs to one of three temperatures: hot, neutral, or cold. Hot duplicates the extra warmth provided by the mother python, and cold duplicates the absence of the mother. Here are the data on the number of eggs and the number of hatched eggs. Make a two-way table of temperature by outcome, hatched or not. Okay, so we want temperature by outcome. Well, the three temperatures we have are cold, neutral, and hot. So there's our column variable. Then we have the eggs are going to do one of two things. They are either going to hatch or they are not going to hatch. And then we can put the total down in this last column. Number of eggs that hatched in cold water was 16. Number that hatched in the neutral water was 38. And the number that hatched in the hot water was 75. Number that didn't hatch, well, take 27 minus 16. That means 11 did not hatch in the cold water. Take 56 minus 38. 18 did not hatch in the neutral water. And 104 minus 75 means that 29 did not hatch in the hot water. And then if we add those up, we should get back to our totals of 27, 56, and 104. Now from our two-way table, we can begin answering some questions. So looking at the next slide, calculate the percent of eggs in each group that hatched. The researchers anticipated that eggs would not hatch in cold water. Does the data support that anticipation? Well, let's start with the cold water. In the cold water, 16 out of 27 eggs hatched, which is about 59.3%. In the neutral water, we had 38 out of 56 eggs hatched, which is 67.9%. And in the hot water, 75 out of 104 eggs hatched, which is about 72.1%. So the researchers anticipated that eggs would not hatch in cold water. Does this data support that? Well, no, it doesn't. So if we look at the cold water only, about 59% of the eggs in cold water still hatched. What can we say beyond that? Well, we can clearly see that as the water temperature increases, or the nest temperature increases, however you want to say it, that we get a higher percentage of eggs that hatch. As the nest temperature increases, so does the percent of eggs that hatch. Okay, Simpsons Paradox. Accident victims are sometimes taken by helicopter from the accident scene to the hospital. Helicopters save time. Do they also save lives? Let's compare the percents of accident victims who die with helicopter evacuations and with the usual transport to the hospital by road. Here are the data that illustrate a practical difficulty. Okay, so we have whether the patient was taken by helicopter or road is our column variable. Whether the victim died or survived is our rho variable. We can see that about 32%, or 64 out of the 200 helicopter patients died, compared with only 24%, 260 out of the 1,100 of the others. That could seem discouraging if we only look at the data in that manner. The explanation is that the helicopter is sent mostly to serious accidents, so the victims transported by helicopter are more often seriously injured. They are more likely to die with or without the helicopter evacuation. Here are the same data broken down by seriousness of the accident. So we have serious accidents on the left, so we're introducing a third variable that we're dividing this data up into, and less serious accidents on the right. We still have then within each one of those categorical variables of the seriousness of the accident, whether they went by helicopter, by road, and whether they died or survived. If we inspect these tables to convince yourself that they describe the same 1,300 victims in the original two-way table. For example, 200 were moved by helicopter, 64 total died. So if we look at those that are moved by helicopter, we have 100 here and 100 here. And if we look at the total that died, it is still 64 patients. So it's the same data, just separated by this third variable of the seriousness of the accident. If we look only at less serious accidents, back up. Among victims of serious accidents, the helicopter saves 52%, or 52 out of 100, compared with only 40% for the road transport. Okay, so we're looking only at serious accidents. 52 out of 100 survive when they're transported by helicopter. 40 out of 100 survive when they are transported by road. If we look only at less serious accidents, 84% of those transported by helicopter survive. So we have 84 out of 100 versus 80%, 800 out of 1,000 transported by roads. So both groups of victims have a higher survival rate when evacuated by a helicopter. And that takes us to what Simpsons Paradox is. An association or comparison that holds true for all of several groups can reverse directions when the data are combined to form a single group. This reversal is called Simpsons Paradox. The lurking variable in Simpsons Paradox is categorical. That is, it breaks the individuals into groups, as when accident victims are classified as injured in a serious accident or less serious accident. Simpsons Paradox is just as extreme, an extreme form of the fact that observed associations can be misleading when there are lurking variables. So the third categorical variable we introduced here was separating the data now by serious accident and less serious accident. When we separated it by the seriousness of the accident, okay, we found that helicopter transportation saved a higher percentage of lives than the road transportation. However, if we combine all that data together and don't separate it by accident, it shows just the opposite, and that's the idea of Simpsons Paradox. Upper Wabash Tech has two professional schools, business and law. Here are two-way tables of applicants to both schools categorized by gender and admission. Although these data are made up, similar situations occur in reality. And if you read about this in your book, it's a situation in which a college was sued because of its admission standards, and during the trial, Simpsons Paradox was brought up in the course of the trial to show that the reason that they were being sued was really not a valid reason, and you'll see that same thing here when we go through this problem. We want to make a two-way table of gender by admission decision for the two professional schools together by summing the entries of the two-way table. Okay, so here we have three categorical variables. We have students applying to the business school, students applying to the law school, whether they were admitted or denied in each one, and then whether they were male or female. We're going to combine these two separate tables into one table by combining the data. So now we are only going to talk about students in both colleges, the business college and the law college, whether they were admitted, whether they were denied entry, and then whether they are male or whether they are female. How many males total were admitted? Well, add them up. There were 490. How many males were denied? Add those up, 210. How many females were admitted? 280. How many females were denied? 220. So there's our two-way table when we combine that data. Okay. Next question. From the two-way table, calculate the percent of male applicants who are admitted and the percent of female applicants who are admitted, and show that Wabash admits a higher percentage of male applicants. Well, let's start with the males. Male applicants, we have 490 admitted out of a total of 700, showing that they admit 70% of the males that apply to their university. Female students. There are a total of 280 admitted out of 500. They only admit 56% of the females. So looking at that data, seems that they admit a higher percentage of males than females. So this could be grounds for discrimination, that they are admitting a higher percentage of males than females to their university. Now compute separately the percents of male and female applicants admitted by the business school and by the law school. Each school admits a higher percentage of female applicants. So let's look at each one individually here. Let's start with the business school. If I look at the business school for males, in the business school for males, 480 out of 600 males that apply get admitted. That's 80% of the males. For the females, 180 out of 200 females get admitted. That's 90%. So we can see in the business school, they actually admit a higher percent of females than they do males. Let's look at the law school. In the law school, they admit 10 out of 100 males, or 10% of the males. Females, they admit 100 out of the 300 that apply. They admit 33%. So at the law school, they admit a higher percent of females than males. So you can see the difference here, and this is the crux of Simpsons Paradox. If I look at all of the data together up here, okay, overall, there's a higher percent of males that apply to the university that are admitted than there are females. But if we break it down by each of the individual colleges within the university, the College of Business and the Law College, in each one of those individually, they're actually admitting a higher percentage of females than they are males. This is Simpsons Paradox. Both schools admit a higher percentage of the women who apply, but overall, Wabash admits a lower percent of female applicants than of male applicants. Explain carefully, as if speaking to a skeptical reporter, how it can happen that Wabash appears to favor males when actually it individually favors females within each of the individual schools. Well, the problem is, where are most of the males applying? Well, 600 of the 700 total males apply to the business school. So that means 6 out of 7 males apply to the business school, which admits 82.5% of all applicants. When I look at the females, 300 of the 500 total, so 3 out of 5 females apply to law school. which admit only 27.5% of all applicants. So we can see that because there are a higher percentage of females applying to the law school, and the law school only admits about 1/4 of the students that apply, that is why when we combine the data and look at it, that it looks like there are a higher percentage of males being admitted, when in reality there's a higher percentage of females within each school that are being admitted to the university.